Good morning, everyone. Our topic today is modeling hemorrhage, a differential equation approach. Imagine an emergency surgery where every second counts. How can mathematics help doctors decide when to stop infusing saline and start a blood transfusion? That is what we're going to explore today. As reporter is Chen Mohan and Huang Bowen. Here is our agenda. I am Huang Bowen, and I will focus on Part 1, building the mathematical model and the derivation. Then my partner Chen Mohan will take over for Part 2 to show you the analytical solution and our Python simulation. Let's start with the scenario. A patient is losing blood during surgery. To maintain blood pressure, doctor infuse saline solution. But there is a conflict. Saline keeps the volume up, but it has no red blood cells. It dilutes the blood. If the RBC concentration drops too low, the patient will go into shock. Our goal is to use calculus to predict exactly how much time the patient has. So the context is emergency surgery and the conflict, hemorrhage, and saline infusion. The risk, dilution of RBCs, and then patient gets shocked. Our goal is to predict the survival time using calculus. So now to solve this, we simplify the human body into a mixing tank model. So it's like the mixing tank. Imagine the body is this tank. We have saline flowing in and mixed blood flowing out. We make two key assumptions. First, the input is pure saline, so the RBC input is 0. Second, the blood in the body is perfectly mixed at all times. So these are the two key assumptions, and we make a simplification. Now let's define our variables. Vt is the total volume for liquid in the body at time t. Rt is the amount of red blood cells, which is what we want to track. And Ct is the concentration equals to R divided by V. So this is basically our variables. Here is the core logic of our model. The rate of change equals to rate in minus rate out. Let's write the equation. dr over dt equals to rate in minus rate out. Since we are inputting saline, the rate is 0. Rate out equals to outflow speed. Rate out multiplied by the current concentration. Rate in is 0, and rate out equals to R out minus RT over VT. So RT over VT is the concentration. However, we must remember that volume is not constant. It changes based on the difference between inflow and outflow. So Vt equals to V0 plus R in minus R out times T. This is our equation. Substituting this back, we get our final differential equation. dr over dt equals to minus R out times R over V0 plus R in minus R out times T. This equation describes the speed of life flows. Now, have the model. Now we have the model, but can we solve it? And what does the curve look like? I will now pass the microphone to Chen Mohan, who will show you the solution and the simulation result. We have defined the rate of loss, and how do we solve it? Now, it's your turn, Mohan.
Good morning, everyone. My name is Chen Mohan. In this section, we will focus on solving the model. Let's start with the differential equation derived earlier. On the screen, you see the equation for dRdt, which represents the rate of change of red blood cell volume over time. The term on the right shows that the rate of blood loss depends on the outflow rate, that is R out, and the current concentration of cells. The denominator, this one, represents the total blood volume changing over time as we're pumping saline in and lose blood out. To solve this mathematically, we apply the method of separation of variables. As shown here, we move all terms containing R to the left side and all terms containing T to the right side. This step is crucial because it allows us to integrate both sides and strip away the derivatives. After integrating and applying our initial condition, we are at time 0. The RBC volume is R0. We arrived at the general analytical solution. This formula gives us the exact RBC volume at any specific time t. While this formula is mathematically precise, in the real-world medical setting, dynamic visualization is often more useful. This leads us to our Python simulation. Here, we transition to the numerical method. First, we set our parameters. We assume an initial blood volume of 5 liters and an initial RBC volume of 2.25 liters. And most importantly, we define a danger threshold of 1 liter. If RBC count drops below this line, the patient is in critical danger. Next, we translate our math into code. We define a function called blood loss model. This function calculates the derivative dRdt at every single time step. We then use audience to simulate the surgery second by second. So finally, visualization is key. This code block uses Matplotlib to plot our results. We plot the declining RBC volume curve and draw a red dashed line representing the critical threshold. The code also automatically calculates the exact intersection point to predict the time of death or critical failure. Look at this. The blue line shows the steady decline of red blood cells, and the red dashed line is our danger zone. Our model clearly predicts that the curves intersect at approximately 80 minutes, so they have exactly 80 minutes to stop the bleeding before the patient reaches a critical state. We also ran a scenario analysis called the dilution effect. We compared a standard saline drip, this blue line, with a faster drip, this orange line. Notice that the orange line stays higher, but why? Because bumping in more saline increases the total volume, effectively diluting the blood. Although the blood is thinner, the rate of RBC loss slows down because each drop of lost blood contains fewer cells. However, more saline isn't always better because of other risks like fluid overflow. To conclude, this project demonstrates the synergy between math and technology. Calculus models the vital rates of change. Simulation provides real-time decision support. And in the future, we may see this integrating into smart operating rooms for automatic monitoring. So that's all the content. Thank you for listening.